Sound and vibration are a leading indicator of a machine's health. This self-service trial allows you to test OtoSense AI on data collected on your assets. The OtoSense AI platform enables the building of two types of models: anomaly detection and event recognition. With the anomaly detection model, OtoSense learns how a machine behaves under normal conditions. When it has finished learning normal condition behavior, OtoSense can then let you know when it detects something unusual or abnormal compared to the normal signal it has learned. For this type of model, you will need to collect 5 to 10 minutes of normal signal on your machine and also build a roughly 30-second test file where you will put either just the abnormal signal or a range of both normal and abnormal signals. With the event recognition model, OtoSense learns to identify events, which can be various operating conditions of the machine or some of its known malfunctions. For this type of model, you need to be aware of the different signals your machine makes in order to collect and label the corresponding data. When used on a real device, the two models run simultaneously. However, for this trial, you can choose the type of model that best suits your needs or corresponds to your available data. Keep in mind that this tool uses default features to build the models. When in production, the models are optimized for your use case. If you already have recordings, check our requirements to make sure they will be compatible with this tool. If you haven't collected data yet, we invite you to review our tutorial videos. Okay, now that you have chosen the type of model that best suits your needs, how exactly does it work? Let's go back to the event recognition model. In this trial, you can have OtoSense recognize 2 to 5 different events. Because OtoSense needs to learn before it can perform the recognition, we ask you to provide at least 5 minutes of recordings for each event if the signals are stationary, like the sound of a pump, bearings, or of a motor. You can upload several files per event, as long as the sum of the recordings exceeds 5 minutes. If the signal you want to be recognized is transient, like a click or a knock, then you will need 50 different examples of that signal. Again, you can't do machine learning with only a few examples. The more you learn, the better you perform. You will also need to build a 30-second test file that will contain at least 2 events, preferably not using the signals you already used to build your model. If you need a hand to build this test file, check out our tutorial videos. All these sound or vibration files will have to be mono, 16-bit depth, and have a .wav format. OtoSense has been optimized for the Chrome browser, so please use it whenever possible. Okay, let's get started. Click Start Building Your Model. First, I will need to enter a tag for each event to be recognized. For example, here, my first event will be normal bearing, and I select the files I want to upload. I can add one or several files or select a whole directory. Then click on Continue. I will call my second event under Lubricated and upload the corresponding files. You can add up to 5 events. Here, I'm going to enter a third event, Scrape, to describe the signal collected when we found a scrape on the outer ring. Make sure your files contain only the signal of the event. Be careful not to leave silence or chunks of another event in your file. When all the events are uploaded, you can generate the model. The results of the confusion matrix are represented as a chord diagram, along with a statistics table. The categories of events are shown on a disk, with size in proportion to their respective amount of data. The larger the colored areas, the better, because that means good recognition was obtained. Confusions are shown as gray chords linking different categories. In this example, we have only one confusion between normal _ bearing and scrape, and you can see in the table that the performance of this model is excellent, 99 to 100% depending on the tag. It is now time to put the model to the test by uploading my test file, in which I put the 3 events. The device simulator gives you the same output an OtoSense Edge device would provide. You will see under the spectrogram of your test file the OtoSense recognition output, showing which event got the highest probability over each time window. So, for example, between the very beginning of the file until the 11th second, you can see that the event normal_bearing got the highest probability. And then from 11 to 22 seconds, scrape got the highest probability. If you know the signal well, you can play the file while you look at OtoSense output and check that it corresponds to the expected event. The process is even simpler when you want to build an anomaly detection model. In this case, click Start Building Your Model. Then select the normal signal file or files that OtoSense will use as a baseline to build an outlier model. Here, I upload the sound of a normal hot air blower. After that, I select the test file where I have about 9 seconds of the blower when it isn't functioning normally, and then about 12 seconds of normal behavior. Click on Generate and Test Model. Before the results are displayed, you will be able to read the explanation of the plots in a pop-up window. Once you close that window, you can return to it by clicking on the Outlier Score info icon at the top of the page. Outlier scores are presented as histograms under each spectrogram, the top one being your baseline file, the bottom one your test file. Each vertical bar represents a chunk of roughly 1 second when you have a 44 kHz sample rate. Because your test file is much shorter than your baseline file, the bars appear much larger. The threshold above which OtoSense considers a signal abnormal is set at the highest outlier score reached in the baseline. By hovering over the bars, you can see the outlier score for each chunk. Here, the higher outlier score is roughly 2.3. So every chunk in the test file that has an outlier score above 2.3 will be considered unusual. The outlier scores below the threshold are represented in blue. The darker the blue, the closest to the threshold, while the ones above are in red. The darker the red, the higher the outlier score. So all the red bars here correspond to the signals OtoSense considers unusual. Ready? To your files and go!